Good morning, all of you. Thanks for this opportunity. This award is really motivates us to conduct more better innovation for moving sustainable. We've been working on this alpha hydropower conference since for the past 15 years, probably since PhD. And I'm continuing this research with my students. Ultra high performance concrete is basically an advanced cementitious composite, which primarily differs from conventional concrete by eliminating coarse aggregate gravel to improve the homogeneity and crack resistance. So commercially available ultra high performance concrete products are highly expensive. That is the main reason for not using this important material, even with the great benefits it offers, like greater compressive strengths, mechanical strengths, extreme durability. But because of the initial cost, this material is not being widely used in a variety of structural applications. So therefore, we thought of reducing its cost by using supplementary cementitious materials in high volumes. This is the outline of the project of my presentation. I talked about a little bit on sustainability, research objectives, and what are the various curing regimens we used to develop this material, and how do we replace cement with slag up to 60%, and then I'll talk about a little bit of results on durability and mechanical performance that we observed in the laboratory experimentation. As I said, this ultra high performance concrete is basically exhibits compressive strength of greater than 17,000 psi and flexural strength more than 2,500 psi, and tensile ductility strain is almost 3% and a little above 3%, just like steel. Even though high cementitious content is required, but the initial cost can be offset by increasing the surface life of the structure by exactly double, and the thinner cross sections, and especially in longer span bridges, lesser number of structural elements would be required and compared to conventional concrete or high performance concrete structures. So that's how the initial material savings can be possible. But it's a very high density concrete, very less porous, even though the porosity we measured, permeable porosity we measured in the lab is way less than 2%. Even then, those pores are not interconnected. So ingress of harmful ions like chlorides, sulfates are nil. Freeze-thaw durability is excellent. This is the material for the future. Of course, I already talked about advantages and disadvantages. The main thing is high initial cost. All the researchers working on this ultra high performance concrete are basically working towards the reduction of the cost, and high cement content is another issue, especially from the sustainability, environmental sustainability point of view. And for this particular material, some of the raw materials such as silica fume, steel fibers are being shipped from internationally. Sometimes it should be imported. Until very recently, we have to get the steel fibers from China, but after the Buy America law, it was restricted to use steel fibers from the other countries. Even federal government projects has to get the approval for a project waiver to get the steel fibers from China and other countries. But we have one or two companies available now producing steel fibers here. That is another challenge. That's my next step of my research, how to eliminate steel fibers by using some crumb rubber particles, because both are toughening materials. Another thing is, some states, we were surprised that they want to use ultra high performance concrete. For example, Illinois Department of Transportation, they want to use UHPC for their bridge applications, but unfortunately, they do not have an access or a supply of silica fuel. So therefore, that is another drawback. So in all our researches, we have identified all these practical problems, and we are now working on towards solving those problems. So the goal of this research is to develop an ultra high performance concrete that is cost effective and environmentally friendly. So now, alternative to cement, we have two choices, and fly ash and blast furnace slag. There are several researchers fly ash is being used, so we should rethink that why we cannot use blast furnace slag. At the same time, for Slag Cement Association and other slag users, this is a great opportunity because fly ash is slowly disappearing. That's another challenge the entire construction industry has to face now. So we are also working on finding the alternatives to fly ash. One of my research students, Meghana, she is here. She's one of the team members here. She is actually investigating alternative pozzolans to replace fly ash. And now everyone, now we are using slag to replace cement. Now Meghana is trying to replace fly ash with slag in her mixes that is being used for bridge deck overlays. So we'll see how it goes for next year. So the blast furnace slag is basically, we all know it's a byproduct from steel mills. It's a very useful supplementary cementitious materials. It helps reducing the porosity of the concrete and provides greater lateral strength. Obviously, since we are replacing it for the cement, then it helps in reducing the carbon footprint from the construction industry. Now, in this particular research, we have used two different curing regimens to investigate the effect of heat treatment, how the slag stabilizes the cementitious system under the elevated temperatures. So regular one is just in a moist curing room with room temperature and almost 85 degrees relative humidity. And water bath curing is basically simulates simulates the steam curing in precast plants. So basically what we did is that we took a plastic tub with water and placed it in an oven, set that oven at 90 degrees Celsius, and all the specimens were cured under it in a wet curing condition, but at the 90 degrees Celsius to simulate the steam curing. These are the two curing regimens that we investigated. Then, first step in this research is to optimize the slag content. How much slag we can replace. Now we can use to replace cement. So for that, we tested 2-inch cubes for compressive strength at 7 days, and we replaced cement with slag from at various replacement levels up to 75%. And the target compressive strength that we kept in mind is 17,000 psi. That is the any UHPC, any material that can be defined as a UHPC class material if it exhibits a compressive strength of greater than 17,000 psi. So if you look at it, for any replacement level, we achieved strengths 17,000 and above at 7 days. But 17,000, so we have chosen 60,000 is because it is 60% replacement level because it exhibited 17,000 psi, but anything above 60% we have seen workability issues. And we even tried 100% cement replacement too, but workability became very complex issue. We could not able to get workability, even adding 10 gallons per cubic yard of high range water reducing admixture. So we thought 60% is a perfect replacement for cement in the UHPC systems. Then there are some mixed designs here. I'll explain a little bit. PA4, FA4, P stands for plain UHPC, F stands for fiber reinforced UHPC. And another improvement we made in this UHPC mixers is basically in typical UHPC composition, sand that is sieved through ASTM number that is sieved with a particle size range from 75 to 600 microns, which is not a sustainable practice because scalping of sand through ASTM number 30 sieve is a labor intensive process. Plus the material that is retained on top of number 30 is just a waste. So it's not a sustainable practice. So another PhD student worked on this. Then we decided, and from the thorough experimentation, we decided and we concluded that using fine sand is not at all a requirement in achieving UHPC characteristics. Number 4 stockpile sand is just enough. So therefore, in this particular research, we have not used any fine sand, but we just used stockpile sand. The 4 stands for number 4 sand. So the P is plain, A is a series A, F4 is number 4 sand. And PB4, FB4 means plain, series B, number 4 sand. FB4 means fiber reinforced UHPC, series B, number 4 sand. The basic difference between series A and series B is series A is with no slag, series B is with slag. That's the difference. So if you look at it in the series B, we have just used 600 pounds per cubic yard of cement. That is just as conventional concrete level of cement dosage. The cement factor is there is very, very less. And 900 pounds per cubic yard of slag we used. So 40% cement, 60% slag in an UHPC system. And in all of these 4 mixes, with slag mixes and without slag mixes, the flow on a spread table is greater than 10 inches, is way more than enough for the bridge applications. Our research is mainly focused on bridge applications because the currently UHPC usage is mainly in closure posts, bridge deck girders, shear key, grout as a grout material for shear key, all the PB elements basically. That's why we are focusing on all the development of all material characteristics towards the bridge applications. Okay, so basically the A series mixers are control mixers and B series mixers are slag modified mixers by replacing cement from A mixers by 60% with slag to produce B series mixers. I think this is clear. Then that is the flow table test. It's just of overflowing. More than and A series mixers, if you look at it, 0.17 is the water binder ratio. And B series mixes, slag mixes, we could able to reduce the water binder ratio from 0.17 to 0.15, yet achieve the same spread. But slightly 1 gallon per cubic yard increase in HRWR, high range water reducing aid mixer, because slag definitely, it's not like it will not produce like a ball bearing effect like a fly ash. So we should able to increase a little bit of high range water reducing aid mixer, but that's it. But we have had a lot of cost savings and environmental impact reduction by using 60% of slag, because UHPC is a very high cement factor composition. Then permeable porosity we measured. If you look at it, the porosity is drastically reduced using slag. And the control mixes, where there is no slag, the permeable porosity of UHPC is 2.4%, while the slag mixes, B series mixes, the permeable porosity is just 1.1%. That means the slag content, the slag presence of slag reduced the permeable porosity by 50%, which is a great thing for any concrete, basically. And because primarily presence of fibers, curing period, type of curing regimen, cementitious materials are the main factors that can influence the porosity. So for both these systems, the fibers are constant for 2% by volume. Curing period is same. Type of curing regimen is same. But the slag mixes produced or exhibited 50% lesser porosity, which is nothing but the filler effect of the slag that actually helped the reduction of porosity. This is one benefit we have observed. And compressive strengths, if you look at it, the control mixes, average compressive strengths for plain 24,000 psi, fiber 25,000 psi. But the slag mixes produced a little bit lower strengths, 19,000. Obviously, this is understandable. About 20,000 psi with plain mixes and more or less similar strengths for the fiber reinforced mixes. Nevertheless, with the penalty in compressive strength, we saved a lot of cement and cost. And 17,000 psi is very high strength enough, strong enough to apply in the bridge applications. But we are still working on improving these strengths. And later I will show you that we finally hit 24,000 mark even with slag in the next few slides. After next few slides, you will see 17% decrease in compressive strength we observed, but later on we could be able to recover it by doing something else. So elevated curing temperatures definitely helped. Early strength gain even with the slag mixes. Those are some of the broken samples you can see. And split tensile strengths are also both for control mixes. A series and B series slag mixes more or less similar, 2200 psi split tensile strength for this ultra high performance concrete as opposed to 600 700 psi in conventional concrete. And the rapid chloride permeability test we performed to observe the susceptibility of chloride ion penetration. If you look at it, the blue bar is basically with blue bar and with the moist curing, and the orange bars are with the water bath curing. Obviously, water bath curing, elevated temperatures accelerates the early action of pozzolanic material. So, and early hydration of this pozzolanic material slag basically produces secondary calcium silicate hydrates that fills the voids left from the primary hydration of cement, so that enhances the microstructure. So obviously the pore spaces and pore volumes have got reduced. Therefore, the chloride ingress is reduced. So in both non-slag mixes and slag mixes, we observed very low to negligible chloride ion susceptibility. And then we did some freeze-thaw testing. The below is the freeze-thaw cycles that we followed. But in freeze-thaw, we used a slightly different curing regimes. The standard ASTM 666 method A suggests us to do 14-day moist curing and then 1-day curing conditioning. And then before putting the samples into freeze-thaw cabinet, that we followed. And then we tried to simulate the practical conditions, only 7-day moist curing and followed by 7-day dry curing, because no one in the fields will cure the specimens at 14 days, such a long time. It is practically not possible. Therefore, to simulate the practical conditions, we did a 7-day moist curing briefly, and then we just left it for air to see how the freeze-thaw resistance of these UHPC specimens. These two graphs are basically mass versus number of cycles, and the left to my left, to your left, and right one is the relative dynamic modulus, and these graphs are related to A series mixes, non-slag mixes. There is no mass reduction. That means there is no micro crack formation, no material distress inside. That's an indication. And relative dynamic modulus never fall below 100%. So for conventional concrete, your information, if relative dynamic modulus of any specimen falls below 60%, we classify that specimen is failed under freeze-thaw conditions. But ASTM 1857 related to UHPC material, the relative dynamic modulus should not fall below 90%. Because it's a high integral material, so it's not 60% the threshold number, it is 90%. But in this case, we have seen there is no drop in relative dynamic modulus. There is no material deterioration with no slag. Similarly, this one is with slag, same results. No freeze-thaw distress, no mass loss, no relative dynamic modulus drop. So excellent freeze-thaw durability. Then this is the part of the research is still ongoing, and we have successfully replaced cement at this point with slag by 60%. And then now, currently people are, a lot of State Department of Transportations are leaning towards using PLCs, especially in Ohio Department of Transportation, that we are listening the words from various sectors of industry that the Ohio Department of Transportation will be switching to PLCs from next year. So we have to see how slag will react with limestone, because we have to get ready for the practical conditions that can occur anytime in the future. So right now we are only looking at the interaction of slag and cement, but now we have to see the interaction of slag with limestone cement. That's an important point. That's why we caught the point and included in our research. And then instead of using PLC, we are using a dolomite-based limestone powder, plentifully available, which is byproduct and waste material from the crushing of limestone aggregates. So now the limestone is basically acts as a mineral filler. It is not a supplementary cementitious material. We can call it as supplementary material as a mineral filler. Especially in UHPC system, we are using about 1500 pounds per cubic yard of cementitious material with a very low water cement ratios of 0.15. And typically we need 28% of water for completing the hydration. We are 13% less than what we require. Therefore, there is not much hydration can go on longer as conventional concrete. A lot of unused cementitious binders will be left and they will be acting as filler rather than binding material. Why should we waste that supplement cementitious materials like cement, slag, or fly ash? Just because we are just nothing but using them as fillers. So we can take out that portion and use a filler like limestone powder, which is cheap. Right? So therefore, we are trying to now replace cement with the limestone. So these are some mixes I'm presenting here. 1A, 2A series. The 1A series and 2A series has silica fume in it. 1 and 2 series does not have a silica fume in it. The 1A series is you can take as a control mixes, no slag. Slag cements. 2A there are no slag. I'm only presenting slag mixes here. 1 and 1A series. 1 is having cement, slag, fly ash, and silica fume. 1A, everything is same, but having a silica fume of 6% of total cementitious binders. So 63% of cement, 21% of slag out of the total cementitious binder. Fly ash is 16% no silica fume. 1A is only difference is 6% of silica fume to see how it goes with lime, because we are extracting cement further. We're eliminating cement further by limestone. So we need to have a little bit of silica fume here. So if you look at it, there are spread all over with these mixes. I'm presenting the 1A mixer here with 6% silica. We have achieved 10 plus inches, more than 10 inches of spread with 7 to 8 gallons of high range water reducing admixture. So flow is fine, and we are achieving the strengths of 19,500 psi for plain mixture, 1A mixture with the 6% silica fume. And when we introduce fibers, the compressive strength increased to about 22,000 psi. So no significant strength decrease we have observed with the increase in limestone powder content we varied the limestone powder content from 0 to 25% replacement of cement, only cement. But we have not seen a significant strength decrease. But that means limestone powder is interacting properly as a mineral filler in the presence of slag. It's a preliminary investigations just to present what we are doing. It's an ongoing work, but there is a lot of things. A lot of work is still pending. And if you look at it, the compressive strengths of plain UHPC, fiber UHPC here, 20,000, 22,000. We got increased compressive strengths here, but we have seen no strength decrease with the LP cement combination with slag. And here the limestone powder replacing cement by 15%. That means if you look at it, even though if you look at this mixed design, even though slag showing 21% out of the total binder content, but especially if you count only in terms of cement, here slag replacing cement by 25% and 15% of limestone. So with limestone combination, we are actually replacing 40% of cement. If you want to use limestone powder, as of now, slag can replace cement 25%. And because we want to go up to the maximum potential of limestone powder. If you want to reduce the limestone powder like 10%, then slag can be 35%. It's combination, right? So, but nevertheless, the total cementitious content to cement can be replaced 40% together with slag in combination of limestone. That is our primary observations. And then there are some effect of steel fibers and silica fume here. So, with various replacement levels of limestone powder. Obviously, fiber, if you look at the graph on the left side, the fiber reinforced UHPC orange bar is producing greater compressive strengths when compared to plain. And percentage increase in compressive strength along with silica presence with replacement level. If you see, the greatest compressive strength we achieved at the 10% replacement level of limestone powder when compared to others, but still 15% is a viable option because we are able to produce more than 17,000 psi compressive strengths. Then here finally we hit the target, doing some other things that I will reveal later. So this one is basically finally we received, even with the limestone powder combination with the slags and all, up to 20% limestone powder replacement, we achieved 24,000 psi. And but this is 28-day strength. This is 28-day strength, 24,000, 25,000 psi, comparable with other commercially available UHPC products, where they will be using 1,500 pounds of cement and other cost expensive materials such as quartz powder, sometimes applying presetting pressures, expensive facilities may be needed, but this is UHPC. This UHPC can be produced with your local materials. You can be mixed on your job sites. You can easily train your workforce for your bridge applications or construction applications to make use of great benefits of this particular product. And then we investigated some flexural testing here. We used ASTM 1609 testing, and these are only for fiber UHPC materials, because how the fibers are actually increasing the tensile capacity of the beams. So this is no limestone powder content. There is no limestone, only slag. We got the peak stress here is 2,145. That is modulus of rupture value or flexural strength of this concrete with no limestone powder. This is 10% limestone powder, similar approximately 2,130 psi flexural strength with 10% replacement of cement with limestone. And this is 15% limestone, 2,240 psi. And the residual strength is great, at approximately 50 to 60% residual flexural strength we can get even using a 15% of limestone replacement in combination with slag. That is a great great finding. And then finally, cement can be safely replaced with slag in UHPC systems up to 60% with slag. And if you want to use a slag in combination with limestone powder, 25% slag, and you can use limestone powder up to 20%. And this combination actually improving the density of the concrete too, and resulting in very low permeable porosity and very high resistance to chloride resistivity, we observed. Quaternary blended mixes can be produced like cement, silica fume, slag, and limestone powder. That's the best combination we're thinking, and we have to move forward. And any durability is not at all adversely affected by the use of slag in combination with limestone. And the final UHPC product with a quaternary blend or tertiary blend is a cost-effective and environmentally friendly UHPC that can be produced with your locally available materials and can be widely used in your structural applications. Any questions?
All right. Well, thank you.
Thank you so much.